Let's say that we're tasked with making a diagram that represents the motion of the car as it drives across the road here. That sounds pretty simple. Let's just trace a line segment that follows the car's path and see how that works. The path will trace right under the road. Here we go. Now, if we look at the diagram, we can see that the car traveled along a horizontal path, but we can't see much other information. It doesn't give us any information about things like time, velocity, acceleration. Let's rewind and figure out how we can build a diagram that's going to give us more information. See that drone hovering above the roadway? We're going to say that it has a nice wide-angle camera that can take pictures of the full length of road that we have here. As the car starts moving across the road here, our drone operator is going to snap a picture every second. Each time our camera view box turns yellow, it's going to mean a picture is being taken. We're going to imagine it's happening every second, but to save time, we'll show it at a quicker pace. Our timer is going to be added right here on the bottom left of the screen. And on the bottom right, we're going to take the car's position from each picture and plot it there. All right, here we go. Each picture captures the car's location at that exact moment. And when we put those pictures together, we get a series of snapshots that show the car's position over time. We call this looking at motion in a stroboscopic way. And stroboscopic means showing or capturing the motion of an object at equal time intervals. In our example, we used equal time intervals that were every 1 second, but it could have been every 5 seconds, every 3 minutes, even every hour. We just use whichever time interval best suits the situation that we're working on. So when we look at an object's motion in a stroboscopic way, we can build what's called a motion diagram. And that's what our points plotted on the line segment here create. This is the motion diagram for how our car moved. We use points to represent position on our motion diagram, but sometimes drawings, different types of markings, or even actual pictures of an object are used to plot those position points on a motion diagram. And then how close or how far the points are from each other on a motion diagram gives us information about an object's velocity and acceleration. Let's go over how we can tell if a car is stopped, moving at a constant velocity, speeding up, or slowing down by looking at a motion diagram. This is the simplest situation that we can come across, a motion diagram where the car stays at one position over all of its time intervals. If we only saw one point by itself and we weren't told that multiple data points existed, that wouldn't tell us much. But let's say that we measure the car's position every 2 minutes for a total of 8 minutes. And every measurement lands on that same point. At the starting time, 0 minutes, the car is at this point. It stays at the same position at 2 minutes, 4 minutes, 6 minutes, and 8 minutes. I stacked the points here to make things visually easier to see, but if this was a drawn diagram, we wouldn't be able to stack. We would have to rely on the total information that we're given. But since the car is staying at one point, that means that it's stopped and its velocity and acceleration are both 0. Next, let's look at a motion diagram where the car is moving at a constant velocity. A couple reminders here first. In physics, we typically assume that an object starts at position 0 and time 0, unless we're told otherwise. We also usually call motion to the right the positive direction and motion to the left the negative direction. Okay, so our car in this situation is moving at a constant velocity. The velocity is not changing, it's staying steady. Let's go ahead and understand how this is shown in the motion diagram. All right, remember the average velocity is the change in position divided by the change in time. That means final position minus initial position divided by final time minus initial time. In motion diagrams, we always have equal time intervals. So if a car travels the same distance each time interval, that means that the velocity stays the same throughout the diagram. Let's go ahead and calculate this out for a couple intervals to make it clearer. Let's say that our time interval is 5 seconds. So we're snapping position points every 5 seconds. So we're using our first point and our second point. We see that our first point starts at position 0 and time 0. That's its initial position and initial time. Then we move to our second point, which is at position 4 and time of 5. That's our final position and final time. For position, we're going to use the unit of studs, since we're counting based on the number of Lego studs. And for time, our unit is seconds, like we said. So we have 4 minus 0 studs divided by 5 minus 0 seconds. That gives us 4/5 studs per second. That's the average velocity for that first time interval. Now let's look at the average velocity from the second point to the third point. The initial position is 4 studs and the final position is 8 studs. The initial time is 5 seconds and the final time is 10 seconds. Now we have 8 minus 4 studs divided by 10 minus 5 seconds. Again, we get 4/5 studs per second. We can count to see that all of our distance spacings here are the same. And we know that motion diagram time spacing has to be the same. So anywhere along this motion diagram, the car is going to be moving at the same velocity, that 4/5 studs per second. And it's moving to the right, so it's moving in the positive direction. That means the velocity is positive 4/5 studs per second. Just like in regular math and physics, we don't usually need to put in a plus sign to show that things are positive. We only need to put in negative signs to show things are negative. But I'm going to go ahead and put the positive signs in just to help us visualize directions as we start talking more about velocity and acceleration in these diagrams. Speaking of acceleration, let's go ahead and determine what the acceleration is in the diagram we have here. Since acceleration is a change in velocity over time, and our velocity is staying constant, it's not changing, that means that the acceleration is 0. All right, just to sum things up, the car is moving in the positive direction, its velocity is constant and positive, and its acceleration is 0. Let's get a quick visual of what that motion looks like. So yeah, a steady velocity. And the car stops at the end because the diagram stops there. It's the last stroboscopic picture we take. It doesn't mean that the car was slowing down or stopping. It just means that it's the end of our data. Next, let's go ahead and look at a motion diagram that shows increasing velocity. If you look at the spaces between the points, you can see that they're getting larger across the diagram as we move to the right. First 3 studs, then 5, 7, 9, lastly 11. Let's say our time intervals again are every 5 seconds. Just like before, the numerator in our average velocity equation is the change in position and the denominator is the change in time. That change in time is going to stay equal across all of the intervals. The change in position is getting larger and larger. That means our numerator is getting larger and larger. So that corresponds to the velocity getting larger and larger. Increasing velocity means the car is speeding up as it moves to the right, which is the positive direction. Now let's see what we can find out about the car's acceleration. For now, we're just going to focus on the direction of the acceleration, if it's positive or negative, not whether it's increasing or decreasing. And then again, acceleration is a change in velocity over time. Since the car's velocity is increasing in the positive direction, the acceleration is also in the positive direction. Think of acceleration kind of like a string that's pulling an object in one direction or the other. If the speed of the object is increasing, the acceleration is pulling it in the same direction. To sum up this one, the car is moving in the positive direction, the velocity is positive and increasing, and the acceleration is positive. Let's look at this motion here. So you can see the car is moving a greater distance during each time interval. Next, let's look at the opposite situation, a motion diagram showing decreasing velocity. And again, we're going to assume time intervals of 5 seconds. Now our distances traveled are decreasing from 11 studs to 9 studs to 7 studs to 5 to 3. Just like before, our denominator, that change in time, is going to stay the same across the intervals. But now our numerator, the change in position, is decreasing as we move across our intervals. That means the velocity is getting smaller and smaller as we move across. This means the velocity is decreasing. Our car is still traveling in the positive direction, so the velocity is still positive, but it's getting smaller. Again, we have a change in velocity. Since we have a change in velocity, there has to be an acceleration. When an object is slowing down, sometimes it might be called deceleration. But basically, since the car's velocity is decreasing while it's moving in the positive direction, the acceleration must be working in the opposite direction. Again, think of like a string pulling it in the opposite direction to slow it down. That means the acceleration is pointed in the opposite direction of the velocity. Here's a look at the motion. To sum up this one, the motion and velocity are in the positive direction, but the acceleration is in the negative direction. But even if you're not given distance values or time interval values, you can still look at a motion diagram and see how the motion is or isn't changing. All you need to do is pay attention to the distances between the points. Let's go ahead and summarize all of that. All right, if an object stays at one position over multiple time intervals, velocity and acceleration are 0. If the spacing between points is equal, the velocity is constant and the acceleration is 0. If the distance between points is increasing, the absolute value of the velocity is increasing, but whether it has a positive or negative value depends on the direction of motion, and our acceleration is in the same direction as our velocity. If the distance between the points is decreasing, the absolute value of the velocity is decreasing, but whether velocity is positive or negative depends on the direction of motion, and our acceleration is in the opposite direction of the velocity. Now let's take a look at a new situation where the motion diagram has multiple types of motion, and we'll describe things for each section. We have our puppy here, and its food and bone are on the other side of a field. The diagram shows the motion the dog took to get from its starting point here over to its food. What we want to do is describe the motion in each of the labeled sections. The first thing to notice is that the dog is moving to the left. That means it's moving in the negative direction. All right, in section A, all the distances are equal. That means the dog has a constant velocity in the negative direction and 0 acceleration. For section B, the distance between the points is increasing. That means the dog's velocity is increasing in that direction, in the negative direction. That means the acceleration's in the same direction, the negative direction. Now let's look at section C. Here, the distance between the points is decreasing. The dog's velocity is still in the negative direction, but it's decreasing. Since the dog is slowing down while it's moving, the acceleration needs to be in the opposite direction of the velocity. So the acceleration is in the positive direction. Now in section D, all of our distances are equal. That means the dog is back to moving at a constant velocity, but still in the negative direction, and it has 0 acceleration. Here's a look at the dog's motion. One more question here. Sections A and D both have constant velocities. Which one has the larger velocity magnitude? Magnitude means absolute value, so we don't need to worry about the negative sign. We just want to know which section has the bigger velocity number. That would be section D because it has larger distances between points than section A, and that gives it a larger average velocity magnitude. At some point during this, you may have thought, can't we just make a video of an object instead of making a diagram? In some situations, that might be something we can do. But a motion diagram helps us focus on an object's positions at specific equally spaced moments in time. And in physics, a lot of times we study things that are hard to record directly. That could be things that are extremely small, really big, or moving really fast, or maybe changing directions really quickly that makes them hard to get clear video. In those cases, researchers have to work with data from sensors and measuring tools to be able to graph out an object's motion to see how it was moving. We're learning about motion diagrams with typical everyday objects so that we can understand the method. But once you understand how to do things, you can use those same skills to work with more challenging objects and situations later on.